right, everyone, hopefully you all tried the warm-up before starting the video. Today our warm-up is pretty much going over factoring quadratics. Now, it is important to remember how to factor quadratics because what we're going to be doing today is we are going to extend it to factoring quadratics where there is a trig function in the place of the x. So what we want to do is first we want to start by saying, how do I factor number 1? Now, if we look at number 1, what's nice about number 1 is if I take a look right here, my a value is 1. And when our a value is 1, we do what we call basic factoring. And we tell ourselves we need to know what adds to 2 and multiplies to 1. What values do that? So I'm saying to myself I need to know what adds to 2 and what multiplies to the value of 1. And right off the bat, hopefully everyone noticed, so it's just nice and basic. 1 times 1 is 1. 1 plus 1 is 2. So that worked out. So now what I need to do is say, okay, well those are my factors 1 and 1. Since it's basic factoring, I can write 2 binomials where because I have an x squared term, I would have an x in the first position of both binomials, and then 1 and 1 are my factors. I'd have x plus 1 and x plus 1, and that would be my solution. Now that's nice and simple because our a value is 1. But now we want to ask ourselves, what happens when our a value is 2? And if we go back to Algebra 1 or Algebra 2, depending on your teacher, you might have called it the rainbow method, you might have called it Billy's method, but you tend to take the leading coefficient, which is 2, and in a quadratic equation, the leading coefficient is always attached to your x squared term, and your constant, a constant that stands alone. And we would multiply the 2. We'd take 2 times 3, and that would result in 6. Then we said to ourselves, what adds to 5 and multiplies to 6. So we're doing the same concept here, but then it's slightly different after. So I would say what adds to 5 and multiplies to 6. And when we think of our basic numbers facts, we would say, well, 2 times 3 multiplies to 6, and 2 plus 3 adds to 5. So that checks. However, we have to approach this differently because our a value is 1. This 2 and 3, we take them and we break that 5x into a positive 2x and a positive 3x. And then we drop down the first term and the last term. So you're dropping down your x squared term and your constants. Once we do that, we can factor by grouping. You group your first 2 terms together and your second 2 terms together. And in each group, we look for a GCF. So when I look at my first group, I have a 2x squared and a 2x. And I ask myself, what is the common factor? Well, if I look at this, my common factor would not only be 2, but a 2x. So I'm going to factor that GCF out of that first group. If I take a 2 and 1x out of this, I have a factor of x remaining. If I take a 2x out of my 2x term, I have a factor of 1 remaining because 1 is a factor of everything. Now, once I'm done with my first group, I go to my second. And I say I have a 3x and a 3. And I ask myself, what's my common factor? Well, I'm going to factor out a positive 3. Now, if I factor out that positive 3, right here I have an x remaining. If I factor out a 3 here, 1 is a factor of everything, I have a 1 remaining. Now, I look at what I have, and I notice that inside the parentheses, I have a common binomial factor now. A common binomial factor of x plus 1. So now I can pull out that common binomial factor of x plus 1 and look at what remains, and it's 2x plus 3. And that would be my final factored form. All right? Now, what we're going to do now is we're going to extend this to work with trig expressions. And what we're going to do is instead of having our variable of x, we're going to have a trig function in that place. So let's start with an example. And so we're going to factor the trig expression. All right. So let's take a look at a basic one. And we're going to look at a basic one in the sense that we're going to use the same method that we used in our warm-up for example 1. So if I take a look, I'm going to give you sine squared of theta plus 3 sine of theta plus 2. And because my leading coefficient is 1, I'm going to treat this the same way that I treated the problem up here. I'm going to say, wait a minute, my leading coefficient's 1. I can use basic factoring. And I know I have to factor because I have a sine squared, a sine theta, and a 2. This is an expression in what we call quadratic form, where it's in that form of a an x value squared plus bx plus c. So right when we have something in a quadratic form, we're able to factor. So I can still say what adds to 3 and multiplies to 2. And looking at this here, I'm saying to myself what adds to 3 and what multiplies to 2. Same strategy that I used up here. And if I think about it, I'm like, okay, well that's 2 times 1 multiplies to 2. 2 plus 1 multiplies to 3. I'm sorry, adds to 3. Excuse me, adds to 3. So now I say, well, I have my factors of 2 and 1. I can do the same exact thing as I did up here in 1. Except instead of x, I'm going to put sine theta plus 2, sine theta plus 1. And this would be my final factored form. All right? All right, why don't I give you one to see if you can try. So what if I had cosine squared theta plus 5 cosine theta plus 6. Why don't you pause the video right now and attempt this problem by yourself. Okay, hopefully everyone paused and we're going to go through the process again. Now, what makes this process easier than the process we were working with in this number 2 again is that our leading coefficient is 1. If our leading coefficient is 1, we can state what adds to 5 and multiplies to 6. That strategy will apply because we are in quadratic form. So when I look at that, if I look at 5 and 6, when I look at that here, I would say 2 times 3 equals 6. That checks. 2 plus 3 equals 5. That checks. Now right here, because I have a leading coefficient of 1, I now can just break it up into 2 binomials. Cosine theta, because cosine is what is being squared here, plus 2, and then cosine theta plus 3. And that would be my final factored form. All right? Now let's try some other problems. Let's do something slightly different. Now, let's take a look at an example like this. If I wrote, this will be example 3, 1 plus 4 cosine theta plus 3 cosine squared theta. Now, if you guys take a look at this, let's move it down a little, sorry guys. If I take a look at this, you might not like the fact that the squared term is not first. So what we're going to do in a problem like this, if we want to have it as like the squared term, then the regular term cosine, and then the constant, we're just going to rewrite it. So let's rewrite this. And if I rewrite that expression, I'm going to say, I'm going to put that 3 cosine squared theta first. So I'm going to write 3 cosine squared theta, then my just regular cosine term in the middle, and then my constant at the end. And if we take a look at this, this differs because a is 3. A is no longer 1. So we have to go back to whether you use Billy's method or you use the rainbow method. We need to multiply that leading coefficient by the constant. And again, we say to ourselves what multiplies to 3 and adds to 4. And that's the important thing. So what multiplies to 3 and adds to 4. And if we think about that, I'm obviously giving simpler numbers. We're going to say, obviously, 3 and 1. 3 times 1 multiplies to 3. And 3 plus 1 adds to 4. So that checks. But because a is 3, we're not going to just break it into 2 binomials immediately. We must use the factor by grouping method. So you take this 4 cosine and you break it into, using these values, 3 cosine theta, a positive 3 cosine theta, and a positive 1 cosine theta. And then we bring down the first and the last term. Now, once we get there, we are going to factor by grouping. You group the first two terms together and the second two terms together. And we factor out the GCF of each term. Now, if I look at my first group, they share a cosine. So I'm going to factor out a cosine theta. And when I do that, here I have two cosines, so one still remains. So I have a 3 cosine, oh wait, I need to factor out a 3 too, because both of them had 3. Sorry guys. So we're going to factor out that 3 too. So if I factor, we have a common 3 and a common cosine. But because this had two cosines, one of the cosines will remain. Now if I factor out a 3 cosine here, 1 is a factor of everything, so I'm going to have a +1 that remains. Okay. Now look at your second binomial, and if you look at that, your GCF would be a +1. And what remains? If I take out this +1, I'm going to have a cosine theta. If I take a 1 from here, I'm still going to have another 1 remaining. So if you look inside your parentheses, you have a common binomial factor now. So we can factor out that common binomial factor. And what remains? A 3 cosine theta plus 1. And this would be your factored 1. So that one's a little trickier because we're dealing with an a value that is not 1. All right, guys? Now there's one other thing I want to make sure that I review here. Is I can have a secant 4 theta minus 1. Now, we talked last week about the difference of two squares, and we reviewed that difference of two squares formula. And that difference of two squares was if I had a squared minus b squared, it would be equivalent to a plus b, a minus b. But the problem here is I have a secant to the 4th. But what is secant to the 4th the same as? Well, when we take something to the 4th, it's actually, watch, if I had a to the 4th, that's the same as saying a squared to the a squared squared. So, when I look at that, a squared squared would be equivalent to a to the 4th. Therefore, secant squared theta squared would be equivalent to secant to the 4th. So if I look at this, I can use my difference of two squares. I can say secant to the 4th would be equivalent to secant squared theta plus 1 and secant squared theta minus 1. Now guys, let's see if you have your cheat sheet. If you have your cheat sheet, you should identify one of your Pythagorean identities right now. And if you took a look, you would notice that this secant squared theta minus 1, that is a Pythagorean identity. That is the same, if you look at your cheat sheet, as secant squared theta plus 1 times tangent squared theta. And this would be your final solution. Now, the reason we took this one a step further is because I was able to identify a Pythagorean identity. In the other factored problems, there was no Pythagorean identity there. All right? All right, so now that same concept can be applied if I gave you something like this. If I gave you cosecant to the 4th theta plus 7 cosecant squared theta plus 12. This is, again, this is still quadratic form. It's just that we have a 4th and a square. So that means when we break this up, again, this works out nicely, that our a value is equivalent to 1. So we say what adds to 7 and multiplies to 12. And we're still looking at that, what adds to 7 and multiplies to 12. If I take a look at that, guys, what's going to happen here is I'm going to say, well, what two values do that? My two values that do that are 3 and 4. So I have 3 plus 4 is 7, check. 3 times 4 is 12. And we know it's the basic factoring method because a is 1. But the only difference is because we have a 4th here, instead of binomial starting with just a cosecant, it's going to start with a cosecant squared theta. So it'll be cosecant squared theta plus 3 and cosecant squared theta plus 4. And we would be done here. The reason why is that these are not on our cheat sheet. They are not Pythagorean identities. We are done and in factored form. All right, good job. I hope you guys understood the lesson today. What you have now is you have a WebAssign. It is a 2-problem WebAssign that you need to complete, and that completion of the WebAssign will be your attendance for the day. So please make sure you complete it, and it's based on this information. If you have any questions or concerns, please reach out to me during my office hours, which have been posted on Canvas. In addition, guys, I handed out that packet last Friday, and that packet is due Wednesday for completion. So please make sure that you have it done, and in order to hand it in, you can either hand it in on Canvas or email the completed packet to me. You know, obviously just take a picture so that I can see all your work and I can give you credit for it. If you have any questions or concerns in the packet, please come to the Canvas chat during my office hours, and I will be available for help. All right? Have a good afternoon, guys. Bye.